if you summarize that, it's just a FS Fourier series. Yeah, Fourier series analysis. Yeah, we will talk about that. And try to review like chapter 3, Fourier series representation for periodic signals. Actually, you can see periodic signals we just talk about in chapter 2 and chapter 1, and it is just we talk about in the time domain. But in this chapter, we talk about it in the Frunze domain. Yeah, we try to like represent the periodic signal in Frunze domain. And this first domain, we call it a Fourier series representation. Actually, next chapter 4, we will talk about the Fourier transform representation for any signals. Yeah, like I will tell you the difference between Fourier series and Fourier transform. Usually, the Fourier series is specific for periodic signal, and the Fourier transform is for the any signals. Yeah. Okay. And like the Fourier series, in this chapter, we will talk about FS computation problems. Do you remember? We will try to find the Fourier series coefficient, and then we will try to find out if we know the FS coefficient. We will try to use the signal synthesis to represent the signals. Yeah, those problems we call it FS computation problems. And then we learn a lot of FS properties. Yeah, actually, what's the purpose for these FS properties? Do you remember?
To help us get our FS coefficient.
Yeah, actually, help us to get FS coefficient. Yeah, easily, simply. Yeah. Okay. And then we will do more problem solving exercise for midterm 3 on April 8th. I just decided on like Wednesday. Is that okay? Okay. Okay. And let's try to try to review. Firstly, let's try to review like FS signal analysis. Yeah, actually, for the FS representation, we talk about two different equations. One is what? Do you remember? One is FS synthesis.
The synthesis is the sum.
Yeah. Yeah. And one is FS analysis. Yeah. But here, the FS signal analysis is different with the FS analysis. Yeah, there is a signal, which means for the FS signal analysis, it includes those two parts. Yeah, this is if I write down a signal like this, what kind of this signal? What kind of? You can see it, you do a time shift, but you can see those two signals is same, equal with each other. What does that mean? Which means after you time shift, it's equal. It's the same thing. What does that mean? Which means it's periodic. Which means over t is the same value. Over t is yeah. That makes sense to you? Yeah. When we write down this signal, which means this signal is a periodic signal. Okay. And then for the fundamental frequency, we know like it's 2 pi over t. Am I right? And then for the fundamental like we know like the FS synthesis based on the different basic fundamental like harmonics. Am I right? This is just the basic harmonics. Why we call it basic harmonics? Because you can see here it is omega naught, which means it is a fundamental frequency. Am I right? But actually, the FS representation, which means the signal can be organized, can be generated from a bunch of harmonic signal. Yeah, a bunch of, which means this key will change from negative infinity to the positive, but it should belong to the integer number. That makes sense to you? Okay, and then for this, we know like this is a fundamental like harmonics atom. Actually, we can use this one to calculate the AK. What's AK? Yeah, FS coefficient, and we call this like equation, like FS synthesis equations. And then if we know like signal analysis or FS analysis, this is my pronunciation. No, very and then if we know the AK, what we can know? Actually, the signal. Am I right? FS representation. We can use this one. Yeah, because we know like the AK, then we can represent the original signal in the Fluence domain. Yeah, that makes sense to you. And this we call it signal synthesis. And then actually this signal and this signal is the same thing. Yeah, one is just like in the time domain, one is just in the Fluence domain like that. Yeah, that makes sense to you. Okay, and then it just connect with FS coefficient. Okay, let's try to review 3 FS related problems. Do you remember which 3? Which 3?
We're going to use the
GFT? Yeah, just be brief. Yeah.
So we're going to like use the initial ones, the latest, like what's it called?
Oh, you mean the function of sinusoidal signals? When we talk about the harmonics, we know like the signals, periodic signals also usually generated from a bunch of sinusoidal signals. It's just the definition. Yeah, actually 3 FS related problem, which means three different types of problems related to FS representation we usually want to resolve. Yeah, I think you just think too much. Yeah, this one. The first one is I give you FS coefficient, let you find the signal. Just I give you the FS coefficient, let you find the signal, and then what equation you will use? Yeah, synthesis. Yeah, actually you can see I give you, this is an example. I give you the FS coefficient, and then you use the signal synthesis to like represent the signals. And usually we want to like represent the signal using the sinusoidal form. Yeah, because it's easy for us to analyze. And what equations you will use if you want to transfer the exponential Euler equations. Yeah, just remember that when you have the midterm, you'd better to put down the Euler equations in your cheat sheet. Okay, and the case 2, given a signal composed of sinusoidals, find FS coefficients. Yeah, which means I give you a signal like this signal, and then let you to find the FS coefficient. Yeah, how can you do this? How can you resolve this problem? Yeah, signal analysis. But you know, like for the signal analysis, there is an integration thing. We don't like this. We usually don't like integration because it means some complicated computation. Yeah, for this one, actually, there is a trick.
So we're going to find a common period.
Yeah.
We're going to have 3 and the like 2 and then
yeah, I think maybe you got that. Yeah, you can see for the sinusoidal signals, we can use Euler equation, transfer the sinusoidal signal to exponential signal, am I right? Exponential complex function, which means you can try to transfer those parts to the like exponential function, am I right? For the exponential function, you can use signal synthesis to compare and then find the FS coefficient. Does it make sense to you? Yeah, actually, after you transfer this to the complex signals, and you will find you can easily to get the FS coefficient. Yeah, you don't need to use the signal synthesis equations. Okay, and then you will have this FS coefficient very easily. Yeah, that makes sense to you. Okay, the third one is the difficult one. It's just we mainly focus on. Yeah, given an arbitrary signal, find the fs coefficient. Yeah, then you will use the signal analysis. Yeah, actually, this arbitrary signal is not any signal. It's arbitrary periodic signal. You need to pay attention to that. Yeah. Okay. And then we just use the signal analysis. But as I talk about that, we don't like the signal analysis equation because it includes integration. Am I right? Then what we can do? What we can do? Do you remember? We just use two often used FS pairs, and then functional properties. Yeah, some properties you can use. Yeah, this is the second one we usually talk about, and you can get the AT. And A now, it's just like a 2T1 over T. Yeah, I didn't put it, but you can. Yeah, and this is the other one. And those two actually is not enough for you to find an FS coefficient for any arbitrary periodic signal. You need to use properties. Yeah, that's the reason why we want to learn properties. That makes sense to you? Okay, and then let's try to review FS properties. Yeah, actually we learn a lot of FS properties. Yeah, and for these FS properties, we still based on the signal synthesis and the signal analysis. If you want to prove these properties works or it is right, you usually based on that. Yeah, that makes sense to you? Okay, and then what properties we learn? Do you remember? Distributive is convolution. Yeah. Yeah, time shift linearity. Yeah, am I right? And then symmetric. Yeah, symmetric properties. And then integration, differentiation. You remember? Yeah, and the time reversal, time scaling. Yeah. Yeah, the first one we talk about the symmetric properties. Yeah. And then we talk about the linearity and time shift. And then we talk about the differentiation and integration. And then we talk about the multiplication. Yeah. And the last one, we just talk about scaling conjugate in the last class. Yeah. And then actually those properties help us to resolve all those find the FS coefficient for the any arbitrary periodic signals combined with those two very often used FS pairs. Yeah, we talk about many examples. Yeah, okay, those, yeah, you can see, you can use all of these properties to simplify the computation of FS coefficient. Yeah, that makes sense to you? Okay, and actually you can see, for the chapter 3, actually we spend a lot of time on that, am I right? But it seems very simple, right? We just talk about 3 different problems and then try to resolve the case 3, and then we learn many properties. Yeah, the summary is very simple, but the ideas is not that simple because you need to change your what you see for the signal. Yeah, before you just see a signal in time domain. But in this chapter, you need to see the signal in the Franck's domain. Yeah. Okay. Then let's review all the properties. For the symmetric properties, and if the signal is real signal, what does it mean? What's the result? Yeah, AK is A negative K conjugate. Yeah, actually you don't need to remember it. You just put it in your cheat sheet. You need to know that. Yeah, and if you want to know how to improve it, yeah, we improve it like in the class. And for the, yeah, we call it conjugate symmetric. And for the time reversal, yeah, and then we have this one, the FS coefficient equal A negative K. And then for the even signals, we have this one, AK equal A negative K. And then we call it even FS coefficient. And for the odd signals, yeah, we have, this is just the definition for the odd signals. And we have the fs coefficient, this one, a key equal negative a negative key. We call it odd fs coefficient. And then we have, if we have a real and even signal, oh, yeah, waiting for later. Yeah, I will do something. Yeah, and then we have this like a relationship for the fs coefficient, a k equal a negative k equal a negative k conjugate. And then you will find this fs coefficient is real and even. Like, which means if your fs coefficient is real and even, which means your signal is real and even. And then if your like fs coefficient is imaginary and odd, which means your signal is real and odd. Yeah, and then here, usually usually the signals we deal with is real signals. Yeah, the complex signals, yeah, it exists, but for now we don't focus on dealing with it because there is no good mathematical tool for that. Yeah, but the real periodic signals, we have the tool like fs like Fourier series, Fourier transform, we can deal with it. Yeah, okay. And we have more lab for the fs series and fs transform. Yeah, okay. And then the property 2, linearity and time shifting. For the linearity, which means you have two different periodic signals, and then different fs coefficient for the signals. And if you have a new signal, AST plus BYT, which means the new fs coefficient is this. You can easily get the new fs coefficient based on this property. Does that make sense to you? Okay, and then for the time shifting, which means if you have the signal ft fs coefficient is ak, and if you do a time shifting, which means your new fs coefficient is this one, ak multiple this item. And which means here the t now is just this number, which means if your signal is become x t minus 1, which means t now will equal 1, am I right? And you need to pay attention, there is a negative symbol. And if you have t plus 2, which means your t now equal negative 2, am I right? That makes sense to you? Yeah, so which means this one, t now, there will be 2, and this one will be removed. So just pay attention to that. Okay, and then, yeah, we call it linear phase shift because it will try to do a phase shift. Yeah, okay. Then we talk about the differentiation and the integration property. And for the differentiation property, which means you have a periodic signal xt, and the fs coefficient is ak, and its derivative has a fs pairs, this one, and which means your new fs coefficient is this one. You just multiply this part to the xt fs coefficient for the xt. Yeah, this is the differentiation properties. And for the integration properties, which means you have the original xt, and for the integration signal, if you want to use this property, which means the a naught must be 0. Yeah, because if a naught equals 0, and then your yt has your yt is periodic signal, because fs representation only for the periodic signal, right? We talk about that. Yeah. So your new fs coefficient can be obtained by this equation, which means you just try to multiply this part based on the previous fs coefficient. That makes sense to you? Okay, yeah, and then this is a differentiation, and yeah, we just try to analyze why a now equals 0 for that equation. Yeah, any question? No? Okay. The property multiplication. Multiplication, what does that mean? Do you remember? Actually, we talked about in the previous class and the last class. Do you remember? Yeah, which means multiplication which means multiple, am I right? Yeah, which means if you have two different signal, xt and yt, yeah, the fs coefficient is ak and bk. then yeah, this is a periodic signal. Then you can easily to get the fs coefficient for xt multiple yt. Yeah, and you can use this equation to get the new fs coefficient. And this one, actually, we call it dt convolution sum. Am I right? Yeah, because this one is exactly the definition for convolution sum. Yeah, and then we just use this symbol to represent the convolution sum. Yeah, the AK convolution with BK for this equation. Yeah, that makes sense to you. And then, which means the new fs coefficient equal AK convolution with BK equal this one. And yeah, and this is AK. AK you can represent it in the DT signal. Yeah, in this form. And BK you can also represent in this form. And CK you can represent in this form. Yeah, that makes sense to you. Yeah. Okay, and then let's review the last property. Yeah, and the last property we call it. Yeah, this is just the what's this equation's name? Yeah, signal synthesis. Yeah, and then this is just an analysis. Okay, time reversal property, which means if you have a like time reversal like signals, and then you will have this equation, and you will find your fs coefficient is a negative k. Yeah, and then for the conjugate, which means if you have fs coefficient for the xt, and you can easily to get the fs coefficient for the xt conjugate. Yeah, you can. This is just a like a improved process. Yeah, and you will find that the fs coefficient for xt conjugate is a negative k conjugate. Yeah, that makes sense to you. Okay, and then this time scaling, which means if you have the signal xt and the fs coefficient is ak, and then you can easily to get the like x alpha t, the fs coefficient. Yeah, we could talk about that. And do you remember what's the fs coefficient? Do you remember? Yeah, actually, yeah, you don't need to like remember it, but you don't need to memory it, but you need to know that actually the fs coefficient will not change. Yeah, but one thing will change. Do you know what? Yeah, frequency. Yeah, frequency, the period. Yeah, it's the same thing. Yeah, because you can see if you like give a scaling for the t, it doesn't affect this part. It just affects this part. That makes sense to you. And then you just try to yeah, you will find out the period, the frequency will change, but the AK will not change.
So it's like the same signal, just press or.
Yeah, that's like yeah. Okay. Yeah, this is all the properties we learned. Yeah, so many properties, but don't be afraid because I don't want you to remember all the properties. And the purpose for those properties is just help you to simplify your computation for fs coefficient. Yeah, just remember that. Okay, let's try to talk about some examples we haven't finished in last class. Yeah, we have a signal xt and the fs coefficient is ak, and this is time shifting property. Yeah, if you do a shifting and you have the new fs coefficient like this, and then what's the fs coefficient for this signal? Do you remember? Yeah. Do you know how to? Yeah, let's first let's consider a general case. Alpha t minus t naught. Am I right? Yeah, for this one, do you think, yeah, for this one, which means let's considering the time scaling with the new time scaling. What's the fs coefficient for x alpha t? Like what's the fs coefficient? Yeah, since the fs coefficient for xt is ak. Yeah, it's the same thing. Yeah, which means the fs coefficient for x alpha t is ak, also ak, but the period will change. Yeah, it will change the t divide alpha. Alpha, do you know here alpha is what? 3. That makes sense to you? So which means the period is changed. It changes smaller. It will equal t over 3. That makes sense to you? And then let's talk about, you can see, do the scaling first and then do a shifting. Do a shifting, which means here you use this equation, am I right? But you need to pay attention. You have this one, am I right? So you need to change this equation to this form, this signal to this form. Then you can use shifting. That makes sense to you? So which means you just try to put the t minus t naught divided alpha in the parentheses. Actually, it's the same thing. Yeah, that makes sense to you. Then you can use like the fs like a shifting property. Am I right? Which means what's your new fs coefficient? Yeah, you use this one. Am I right? Which means your t, your like a t now, you need to use this part. Am I right? Use this part. All right, you just use this part. That makes sense to you. And t over alpha is just the new period. That makes sense to you. Then you have this one. This is the new fs coefficient for this one. For the, then you can see here, the t period, the new period is equal t divided alpha, right? But did you notice that? Did you notice that? Actually, the final fs coefficient actually is it doesn't relate to the alpha. Did you notice that? Yeah, the it's just the a key. And did you notice that? Yeah, which means no matter you do a scaling, it will not affect the fs coefficient, but it will affect the period. That makes sense to you? Yeah. Okay. Let's continue. Okay. Yeah, this is an example. Let's do a quick review for the important fs properties. Yeah. Still we have the like equation. There is a signal xt and the fs coefficient is ak. And then for the x negative t, we have the fs coefficient will be a negative k. That makes sense to you? And then for the x conjugate t, what's the fs coefficient? Yeah, a negative k conjugate. Yeah, a conjugate negative k. Yeah, the same thing. And if xt equal x negative t, what does that mean? It's an even signal, am I right? For the even signal, we have ak equal a negative k, am I right? And if xt equal negative x negative t, which means odd signal, am I right? Yeah, and then we have ak equal negative a negative k. That makes sense to you? And then for the real, for any signal, the real part, yeah, equal this one. Yeah, we improve that. Yeah, and then we know like we have this equation, am I right here? Sorry, we have this equation and we have this equation and we easy to get the fs coefficient, this one. Yeah, actually there is one properties we use here. It is linear property. Yeah, because this is just a different signal and this is based on the linearity property, we have this one. That makes sense to you? And then, yeah, so this is for the real signal, right? For the imaginary part, if the signal is a complex signal, for the imaginary part, which means you have this one. And then same thing, you have the new fs coefficient for this one. That makes sense to you? Yeah, that's based on the properties we use. And then if you're like if you have this signal xt equal x conjugate t, what does that mean? What does that mean? If xt equal x conjugate t, yeah, that's right. Yeah, but which mean not but what kind of signal it is? actually you can see if xt equal at plus 1, yeah, huh? X conjugate t, x, y, g, yeah, conjugate x minus y, g, for example, right? Yeah, if this equal with each other, which means your y should equal negative y, only when y equal 0, right? Which means you don't have this part. What does it mean? Yeah, it's real. Yeah, when you see this one, it must be real signal, and then you will have you have this one. You just talk about that. Yeah, and also this one, and then we know like all the signals can be generated from the even part and odd part. Yeah, so this for this one, and which means for the even part, we will have the fs coefficient. Same with the real part. Yeah, real part fs coefficient, and for the outer part, yeah, actually this, and we will have the same fs coefficient, which based on this one. Do you know why? Do you know why? Yeah, do you know why? Because those kind of properties. Yeah, if you try to improve that, you will find you can use those properties to improve that. That makes sense to you? Yeah, which means for signals, the real like fs coefficient will relate it to the real even part signal, and the imaginary fs coefficient, yeah, will relate it to the odd part signal. Yeah, that makes sense to you? Okay, and then let's try to talk about example. Give a periodic signal st, and the fs coefficient is ak, and the pair is capital T. Convert a right shift signal xt minus t naught to be a left shift one xt minus plus t1, and show their fs coefficient are the same. Yeah, let's try to deal with it. Yeah, we have this signal. Yeah, which means this one, because any periodic signal, if you shift it, time shifted it, it's still periodic. Am I right? So which means we have this one, right? And then we have this one. That makes sense to you? Yeah, just change the order. And then we will have this one. Yeah, that makes sense to you? Yeah, you can see. Because like the first one is right shift T naught, and like this the second one is just a left shift 1 xt minus plus T1, which means this part, this T minus T naught can be represented like this.
This.
Yeah, which is
like so yeah, it's like there's two signals. You have the first one that's shifted to the right.
Yeah.
The left one is shifted so far left that you put together.
Yeah.
As well, or like it goes left.
Yeah, it can be like if you shift it, it can be like overlap like that. Yeah, yeah, and then you can see the T1 should equal T. And then you can try to like yeah, using if you just yeah, because this part is for this part, and then you will spend T naught equal T minus T1, and then you will find T naught plus T1 equal T, and then which for the xt minus T naught, we have this like fs coefficient. Do you know why here? But because this is T naught, right? This is T naught, T naught equal this one. That makes sense to you? Yeah, it's the same thing. And then, yeah, we have this equation. Yeah, just try to like put everything separate. Yeah, that makes sense to you? Okay. I think here there is a yeah, there is a no, there is no T. Yeah, because T will like yeah. Okay, and then yeah, you can see this one actually is always equal 1 because the GK 2 pi. Yeah, do you yeah, do you agree? Yeah, so you can have this one, all right? That makes sense to you? Yeah, actually you can see this one is exactly this one. Yeah, because you can see if you like time shift, yeah, time shift positive T1, and you use the time shifting property, you can have this one, right? So which means if your T now and T1 have this relationship, and then the Fs coefficient for this one and the Fs coefficient for this one is equal. Yeah. Yeah, the question is just like, we left shift this, have this signal, and we left shift this signal, and in what condition the Fs coefficient will be the same? Yeah, so which means in this condition, this signals and this signals Fs coefficient will be the same. That makes sense to you?
Added together is the same as.
Yeah, it's same with the period, and the Fs coefficient will be same. Yeah. Let's try to.
Well, that makes sense because it'd be like where it starts.
Yeah, yeah, yeah. That's right. Yeah, if you, for example, like for the sun, let me. Yeah. Yeah, you can see for the then function. Yeah, it is a periodic signal, right? You can see if you like time shift half, yeah, like this, and then you right shift, you left shift, like the other half, and actually you will find it's the same thing. Yeah, that makes sense to you. Yeah, and but this is just a simple one. But for the complex one, only if the T now plus T1 equal T equal the period, it will be same. Yeah, that makes sense to you. Okay, and then let's talk about the other one. If we have the other equation, signal x2 equal x1 minus 1 minus t plus x1 t minus 1, then let's try to find the Fs coefficient for the new signal x2t. And then we have this one, we know like the xt have the Fs coefficient ak, and then x negative t will have the Fs coefficient a negative k. Yeah, this is the properties. And then for the x1 t minus 1, the Fs coefficient. Yeah, actually, I don't think. Maybe you just try to like ignore the one. Actually, this is just the x negative 1 minus t. This is x t minus 1. Yeah, I think this will be yeah, this will be right. Yeah, and then for the x 1 t minus 1, the new Fs coefficient, you can use the property, the shifting property to get that, right? Yeah. But you can see this one is easy to get. We can use the shifting property. But this one, yeah, it's not the typical shifting property we can use, right? We can now directly use the Fs coefficient. Then you can see this is just the first thing, we just try to get the Fs coefficient for this one. Actually, for this one, we have this AK, yeah, because just change the negative, right? Because this is T now should equal -1, right? And then compare this one and this one. What's the difference? Do the inverse. Did you notice that? Yeah, which means there is you do time inverse, right? Inversal, yeah. And for the time inversal, yeah, we know this equation. Yeah, that makes sense to you. Yeah, it will equal d negative k. Yeah, it will equal a negative k, g negative j negative k. Yeah, that makes sense to you. Yeah, then we will have the like Fs coefficient for this part, and then this part is just this one. And based on the linearity property, we can have the whole like Fs coefficient, just add them together, and then you will have this one. Yeah, this is just the like that. Yeah, because this is the same thing. So this is just a new Fs coefficient for the like for this x2 signal. Am I right? That makes sense to you? Yeah. So like when I let you to find the Fs coefficient, don't yeah, you can use FS analysis equation, but you will find it's very complicated. Try to use some properties, and you will find it's easier for you. Okay, actually, because give me 1 minute. Let me give you something. Yeah, let's give me 1 minute. Yeah, we need. Yeah. Actually, I have practice. Yeah. And so I just directly from the yeah. Yeah, we have a two Kahoot game. Have you ever tried this before? Okay, and this one. Uh, yeah. Okay. Yeah. So this is just to give you a periodic signal ST with period T equal 4. And let's I give you some FS coefficient. And what is? Okay. Yeah, we have 5 minutes session. That will be enough. Yeah. Okay. Oh, did you? Huh? Oh, yeah. Okay. There is no sound. Okay. Yeah. Let's try to audio. Yeah. What is a symmetric property of XT? You know?
Oh, because they're measured.
Yeah, because you can see, if you want it like even or like odd, which means you just should apply that property. Yeah, but you can see obvious the A negative 1 equal A1, am I right? But A negative 2 doesn't equal A2, which means those two are, yeah, it's not constant, am I right? Yeah, it's not constant, yeah. So which means it's not like a real, okay, let's try to do the next one. Okay. Okay. Yeah. We have 10. Okay. Yeah. Which kind of signal is that? Yeah. Yeah. It is real, but we have already not even now odd. Yeah, it is real because actually, yeah. Okay. And then, yeah. Yeah, how many non-zero FS coefficients are available for the real part XT? Real? Yeah, actually this one is a tricky one. Yeah, because what kind of signal this is? Real signal, am I right? Which means it only have real part. It doesn't have imaginary part. So which means all the FS coefficient is just for the real part. Does that make sense to you? Yeah. And then, yeah, we still have 2 minutes. Yeah, how many now for the imaginary part. I think this one will be easy. Yeah, the real item should be 0, right? Because it's just a real signal. Okay. And yeah, how many non-fs groups are available for the even part of ST? Yeah, even part, which means ST equal X negative T, am I right?
So it would be the A1, A0, and 1.
Yeah, it should be. Yeah. So, yeah, it's a little tricky. Yeah. How many numbers for the out part? Yeah, you know, one signal is just from 0 part, even part and out part, which means, yeah. Okay. And we have, yeah, how many non-zero FS are available for the derivative signal? Yeah. After derivative, A now will be disappear, am I right? Yeah, that's right, because A now just disappear. Yeah, but other items will be there. Okay, and then how many FS coefficients are available for the integrate signal? Actually, this one is a tricky one. Yeah, you know, like if we want to use the integration property, which means we must make the A now equal 0. But here, you know, yeah, so yeah. Which means yeah, the pair is 4. So which one is the right one? Actually, I think this one is the easy one. Yeah. Okay, I think yeah. How many now are available for the new signal x2t minus 1? Yeah, minus 1, which means there is yeah, scale. Yeah, because yeah, you're right. Okay. Oh yeah, this one is skip. I try to delete it, but yeah, I think I just forgot to save it. Yeah, this okay. Yeah, you just skip it. Yeah. Follow the principle of superposition, but this is now this chapter's content. Okay, yeah, just try to use some properties to analyze the signals. Yeah. Okay, and let's have the midterm on next Wednesday. Okay, any questions so far? Okay, how about the homework?
So I still need to get the first one started. I have 7. I'm missing bits and pieces without working through it. And I was like skipping through the parts that I was having trouble with, and I just need to go back and fill in the gaps for
Okay. Okay, that's great. That's good. Actually, I think at the beginning, the signal system and signal seems very difficult for you, but you can see the mathematics is not that difficult. Yeah. Yeah, it's many rules you can follow, and then if you use follow, the mathematics thing is quite easy for you. Yeah. Okay. Any questions? That's a